using the Caret package, right? So there are, I mean, there are a lot of functions which are available in your Caret package, and you can employ almost all the machine learning techniques. Is that? Let me see. Is what about now? Is the voice quality still low, or is there any echo? Yeah. So we'll start off the. So we today's webinar is about uh, your Caret package, machine learning using Caret package. So your Caret package, this particular package, CARET, it stands for your classification and regression training. So if you have any questions, you can use the chat window. We will be taking up the questions towards the end of the session, and please stay on mute. So we have got different, prediction techniques. We have got different unsupervised machine learning techniques. We have got supervised machine learning techniques, prediction models, and so on. A lot of techniques which are present in your machine data analytics or data science. So we will be touching upon a few, and we will be employing linear regression, which is the first regression technique that we normally uh, study when we take up the data science course. This is the first prediction model that we will be building. So when exactly, what is the condition to employ linear regression? Yes, friends. When exactly do you go for linear regression? Yes. What is the condition for your output variable of interest and input variable when you employ linear regression? That is, when you have one input and one output is employed for simple linear regression. Regardless of is it simple or multiple, when do you go for linear regression? What is the condition of your output variable of interest? Is there any condition that has to be met only when you can employ linear regression technique? Yes, friends? Absolutely. Output has to be continuous. Only then you will be employing linear regression. If output variable of interest, the data type, is not at all continuous, then you cannot employ linear regression. Yes? And there has to be some relationship between your output variable of interest and the input variable which is chosen, right? If it is not related to your output variable, then it is not a good input variable to predict the output variable of interest. So you know for a fact that the let me just write down the equation of your linear regression. It is nothing but beta naught is equals, sorry, beta naught plus beta 1 x. This is your y, and we have discussed in our data science course that taking a use case of adipose tissue and waist circumference. This is your y, this is your x, right? So based on different waist circumferences, you will be predicting your adipose tissue, and this equation, you know, is exactly equals to y is equals to mx plus c. M is your beta 1, c is your intercept. So you will be getting a straight line. It's based on ordinary least squares technique, and this is nothing but the equation of a straight line, right? This is what you this is the underlying concept behind your linear regression. whether it is a simple linear regression or a multiple linear regression. And there are a lot of technicalities, a lot of line assumptions involved. We will not be getting into the discussion of the line assumptions. So this is what about your linear regression. Now, in order to employ, do we have, normally what do? We use the LM function, right? We use LM function to employ linear regression. So this comes along with the base package. You don't have to install any package for employing this particular function. This comes from the base package. Whenever you install RStudio, the base package gets installed, and the default functions will be already available. Now, can we do that in your Caret package? Do we have that functionality? Let us see. So I have an R code, I have a dataset. Let me just show you the dataset as well. So Caret is the, first of all, we'll install the package Caret. So Caret is what is the package name. So I have already installed it. I'm just going to invoke it. So this is not required, data.table. This is another package, but as of now I'm not using this package, so I don't have to invoke this package now. Now what I'm doing is I'm calling it the dataset empty cars, which is present in your RStudio. So this is the default, one of the default datasets that comes along with your RStudio in the base package. So I'm just making use of that empty cars package. Now, if I just do a view of empty cars, I will be getting the dataset. So you have got the dataset in this format. You have got different car models, MPG, miles per gallon, cylinder, and all the different input variables. So miles per gallon is my output variable of interest, right? Is your output variable of interest. And then, so what, I mean, we will be looking at what all functionalities, what all functions that we can employ as part of a building a model using the Caret package. So as soon as you get the data, you what do you do, friends? As soon as you get the data, what are you going to do? Yes, we look for, we do exploratory data analysis, and as part of exploratory data analysis, we will be looking for any missing values. If there are any missing values, we will have to impute them, and we will be performing all the steps of your EDA, starting from your first moment business decision to the all the plots and transformations and all those things that can be done. Now, after doing your exploratory data analysis, and within exploratory data analysis, feature engineering also comes, wherein you try to transform the data and you try to come up with some new variables which are relevant to the domain and which are significant in predicting the output variable. Now what I'm doing over here is, again, whenever you build any model, the model has to be built only on the training data, and you have to validate that model on the test data. So for that reason, what I'm doing is, I have got how many observations over here? 32 observations is what I have got. Now I'm dividing this data set into training and test using the create data partition, right? I'm splitting the data set into create data partition, and p equal to 0.6 is nothing but 60% is what I'm looking for. So from this data set, I want 60% of the rows in this object, which is called as your split. So when I run this command, so this create data partition, it will randomly give you 60% of the data. Like you have sample function, right? you have the sample function, right? It is exactly similar to your sample function. You can relate it to your sample function, right? Now, when I run this line of code, I'm getting the split. Now what I'm doing is, from this empty cars, the complete data set, I'm only choosing the observations of split, right? Split has got 60% of the observations from empty cars. So I want just 60% of the observations and all the columns. So that is going to be my training set, nothing but the DEV, the object, and the remaining observation, the remaining 40% of the observations have to be in the validation set. That is, if you just write minus of split, then you will be getting the validation data in this way. So if I just do view of dev, then it's going to give me my training data set and your test data set. Right. So let me see if I have any messages. Yes, create data partition. It belongs to the Caret package. Now, after you divide the dataset into training and test data, then you'll have to employ the model. Now, in order to assess the model, what I'm doing is I'm building the model on the training data. So in order to build a linear regression model over here, my output variable of interest is miles per gallon. So miles per gallon tilde, all the columns is what I'm choosing. I'm choosing all the columns, and I'm declaring my dataset as DEV, which is nothing but my train data, and method is equals to LM is nothing but your linear model. So train function is coming from your Caret package. Using this train function, you can employ linear regression model using LM. If you declare method equal to LM, it's going to employ the linear regression model. So let me see what happens when I run it. Let me look at the output as well. So in this way, this is exactly the similar output what you get when you run the linear regression model, right? So only 1, 2, 3, 4 features are significant over here. Why is that only 4 features are significant? Because we have not performed your exploratory data analysis, right? We have not transformed, we have not looked at the distributions of the data. For that reason, probably we did not transform the data. That's the reason why they are showing to be insignificant. Now this is the summary. Now what I'm doing is, you can also perform cross validation. Just imagine that the model that you have built has given you, I mean, over here you're getting a multiple R squared value which is 0.94, which is very extremely good. But apart from just multiple R squared value, you can also look at the, if for example all these observations, all these features, if they were found to be significant, then in order to confirm that the model is reliable, apart from the accuracy, you can perform cross validation as well. So cross validation is nothing but you are performing the model multiple number of times by taking different samples. So here number equals to a train control is the function which is going to employ the cross validation. It validates the model that you have built, right? So over here, see, if you just go down over here, you build the model once again using this mpg tilde dot, this is nothing but output tilde input variables, data will be empty cars, method is linear regression model. If you give another parameter, train control is equals to this one. So what I'm doing is, before itself I'm running this train control method equal to cv, number of times, number of iterations, or number of times the cross validation has to happen is 10. So if I run this, if I declare, if I if I use this object CTRL in the linear regression model that I have built, you will be getting the output. So if you run that output, look at the summary. Now your cross validation has given even worse results. Earlier you got the better results, but since we did not perform any exploratory data analysis, we did not did any feature engineering, for that reason you are getting these results. But again, when your EVA is in place, and when you have got the distributions of all the variables close to normal distributions, then you will get a good linear regression model with significance of your variables, and even the output of this particular cross validation will be significant. So when you employ this cross validation on any model, it means that apart from whenever you say that your accuracy is 86%, because you assess the model only based on your accuracy. So what happens is, let me just, you whenever you build the model is assessed based on accuracy. But you cannot confirm that this is the a best model that you can come up with, which is going to behave in a similar fashion regardless of whatever data point the new data point comes in. So reliability cannot be confirmed, right? Reliability cannot be confirmed. To confirm reliability, you have to go for cross validation. This can be confirmed using cross validation techniques. So that is what we have employed. For that reason, you have got 86% of accuracy, approximately 87%. So 87% is also good enough to say that the model is good. So you can confirm over here that 87% is a reliable accuracy. So this is about your cross validation. And just a moment, let me go back to the book. Now you can also employ your diagnostics test as well, which you employ in your multiple linear regression. So residual values, you can get the residual values of your friends. I request you to please be on mute.
Mute.
Okay. Now you can get the residuals. What are residuals? Residuals are nothing but the difference of your actual and predicted values, right? What is error or residual? It is nothing but actual value difference your predicted value, or either ways, predicted difference actual values is nothing but residuals. So you're getting the residuals from here. This function resid is going to give you the residuals. So when I run that line of code, I would be getting the residuals. Using the residuals, using this residuals, what I'll be doing is I'll be using these residuals over here in the plot function. Before that, let me also predict the values. So what I'm doing is I'm getting the predicted values from the model LMFit. LMFit is coming from the linear regression model, which without cross validation. So you can also use LMCV fit model from the cross validation, but I have chosen this particular model. So the predicted values from this model is coming from the predict function. If I run this line of code, you will be getting the predicted values. All these are your predicted values. Sorry, these are predicted value. Yeah, now it should display the predicted value. This is the miles per gallon for all the observations, and residuals is the difference of your error and the the actual value and the predicted value. Now what you're going to do is you're plotting the actual value with the residuals. right? So this is the plot that you have got. Is there any pattern over here? Are they random? Yes, friends. Any pattern going on? They're just random, right? And there was a question from, let me see, look at the question. Is cross validation, Nagendra, can be done for linear regression? Cross validation can be done for any model that you build. It can be employed to any, machine learning technique, be it be your supervised machine learning techniques or your prediction models. So you have got the residuals, and if you just draw a line, you can see that the residuals are random. And if you plot another plot using the actual values and the predicted values, this is the plot that you are getting, right? Now just this is about the model that you have built and interpretation of the predicted and the residual values. Now apart from this, you also have an important thing as part of your model building, that is your variable in order to find out the important variables. Finding out the important variables is very important thing. Significance of variables or columns. This can be known. First of all, you'll have to use your domain knowledge, right? You have to use your domain knowledge and consider only the input variables which are relevant. Consider relevant input variables. And say, for example, you have got 30 input variables in this way. So are you going to make use of all 30 input variables? They would not be, all of them would not be required. So probably around 14, 15 or 16, be it any count, not complete 30 variables could be of importance. So there's a way to find out the important variables as well. So how are you going to do that? Variable importance, VARIMP, is going to give you the important variables that were considered in building the model. See, this has contributed 100%, QSEC has contributed 80%, whereas GEAR has contributed 76.17. In that way, you have got different variables. This HP is not contributing at all. So in that way, you have got the variable importance as well. When you plot it, it will display in the a horizontal bar plot. In this way, you will get to know that which are the variables which are important in building the model. And finally, what we are going to do is we are predicting the values. So so far we have implemented each and everything on your training data. Now just imagine that the model that you have built is perfect and you want to predict the value of your test data. For that, you use the function predict. LMFit is the model that you have built on the training data, and you have to predict the values on your test data, which is nothing but your validation. When you run it, the results will be scored in this saved in this predicted val object. These are your predicted values. Now what I'm doing is I'm just preparing a data frame with your actual values and your predicted values. When you run this line of code, you would be getting the output in this fashion. These are your observed values. Observed values are nothing but your actual values. Predicted values are nothing but your fitted values. And this is nothing but the default summary that you get. So RMSE, you know that root mean squared error, R squared value is what we have got. So here you have got the R squared value as 0.58, whereas for your training data, you have got 0.94, right? Do you find any significant difference between your R squared value for your training and test data? There's a significant difference between the R squared values of the training and test data. For that reason, you say that you cannot go ahead with this model, right? So for that reason, what you have to do is you need to perform EDA, spend a lot of time on your exploratory data analysis, and then start off with your model building. And there was a question from Shanu, I believe. Without using cross validation also we can run the model, right? Then what's the use of cross validation? Cross validation is nothing but what it reruns the model multiple times using different samples to confirm the accuracy. For example, if I have run the model, let me tell you that if I have run the model 5 different times, right? 5 different times is what I have run the model. Now you will be getting 5 different accuracies. Yeah, accuracy 1, accuracy 2, and so on till accuracy 5. Now what it does is it computes the average of all these accuracies and gives you the accuracy. So here, and you know, the accuracy should be more or less the same. Cross validation is confirming. Cross validation is nothing but to confirm the reliability of your accuracy. You build only one model and you say that this is my accuracy. Say if you have got the accuracy as 95 percentage or the multiple r squared value, you will jump with joy and say that I have attained 95 percentage of accuracy, the model is best. But when you look at this particular thing over here, when a new data point comes in like your test data, you cannot say that this model is good because you're getting 58 percentage of the accuracy, correct? So in order to confirm it, since we have not performed any exploratory data analysis, we have got a different r squared values over here. If we would have performed all the exploratory data analysis, then we would have got a different r squared values for your by training data and the test data, including the cross validation technique. Cross validation is nothing but to
I want to ask one question.
Yes, please.
I want to ask one question.
Yes.
So this last statement which says actual values and predicted values, you are having predicted. It's just a data frame of 2 columns.
Right.
So what is meant by default summary? How do you get this r squared value? Because it didn't run any model there.
You have, I mean, it what it does is it is computing. I mean, in the background, it is computing. It is giving you r squared based on some mathematical calculation. You can just explore on it. It is calculating these three things: r squared value, RMSE, and MAE is what it is performing using this default summary function. So if you can just do a help of that function, you will get to know regarding the functionality about the function default summary.
Okay.
Right. So this is about the linear regression that we can employ using your Caret package. And then uh, let me also show you another. Let me just close it. Okay. So I have a data set which is of, let me just uh, import the data set to R. So I'll just, since Caret package is already installed, I'll just invoke this package readr, and using this read.csv function, what I'm doing is I'm importing this data set. I have a data set over here which is too huge. Okay, just it's not allowing me to. Equals to C. NA and string as factors is equals to true. You can make use of read.csv or read_csv. Both will be one and the same. So the functionality is the same. So just a moment. Let me just run this line of code. Okay. So let me search for this data set. So I have copied the dataset. The dataset is imported to R. So let me now look at the dataset. So this is the dataset. So it's containing 2,36,628 observations. So this is too huge. And let me look at the dimensions of your training dataset. So it has got 20 features and 2,36,000 observations. So this is the dataset. So it's about a financial data set related to, and the output variable of interest over here is your interest rate. So it's classified as 1, 2, 3. There are 3 classifications over here. Either you have 1, 2, 3. You need to, based on these different attributes, you will have to classify the observations either as 1, 2 or 3. So this is like a supervised machine learning technique, wherein predominantly they are used for your classification techniques. Now from this data set I had and no okay. So what I can do over here is the reason why I have used this NA equal to C of this comma NA is wherever you have, because in this particular data set there were values wherein which was just blank and not NA. So this, for example, if you just consider this value as one which the one which I have highlighted, it was just blank. It was not at all written as NA. So when you import that, it will not be considered as NA. So for that reason, what you have to do is you will have to mention the parameter in this way so that those values will be considered as NA. So what I'm doing over here is you have let me just show you the structure of the data set, structure of train. So these are the number of observations that you have got and the columns. So your interest rate, since it is taking numbers, for that reason it is considering it as integer, whereas it's a factor variable. This is nothing but the classification of different types of interest rates. So it has to be a factor variable, but it is considered as your integer variable. Now what we can do is, and another thing is loan amount requested over here. Loan amount requested here, it can be, in the earlier it was considered as a categorical, as a factor variable, but now it has, it's considered as numerical, so we don't have to change it to as dot integer. So probably what we just have to change the interest rate to factor variable. So using this as dot factor, I'm changing the data type of this interest rate from integer to factor variable. Now since this is of huge size, if we consider the entire data set, so it's going to take a long time for the computation to happen. So from this data set, what I'm doing is I'm just making use of just 5% of the data. So again, I'm making use of this create data partition, using this y is equals to train dollar interest rate. So this, using this interest rate column, give me 5% of the observations, right? So I'm just splitting the data. So from here I'll be getting the split. So if you just do view of split, you will be getting all the observations. But from this train, from this entire train, I just want only split. Then I'm just making use of this train of split is nothing but number of rows and all the columns. Again, I'm putting that in the train object. So this is what you have over here. So when you look at the train data set, you have got 1185 observations and all the variables you have. Now let us look at the number of NA values which are present in train dataset. So yes, so did I have chosen any incorrect? Just a moment, friends. Let me choose the dataset once again. How did it give us? Okay. Fine, no issues. So it says that it does not have any NA values. Probably that dataset is in another machine. So I'll let you know. I'll explain you the package or the function using which you can uh, impute the NAs. So here you normally in imputation what you do is the trend which is normally followed is imputing the NA values. If they are numerical, you impute using either mean or median. This is what is followed by a lot of people. And if it's a categorical data, it is mode what you do, right? Because these are the easier ones to impute, easier functions to employ and impute the missing values. But what happens, I mean, these are the just basic ones to be used to impute the data. Apart from this, you can also use KNN. You can also use your this thing, your linear regression. You can also, there are different packages as well. You have got different packages which are available in order to mice package is another package. HMISC, I believe. Yeah, HMISC is another package. And there are different packages, friends, which are available, which will be imputing, and you will be getting different multiple data sets. Like you will be getting multiple imputed data sets. From those, you will be getting, you can compute the average of these three data sets, and you will be getting the optimal values of the NA values in the, when you take the average of all these three data sets for the imputed values. So in that way, I'm using KNN over here. So KNN, if you just use this pre-process function, it is used to impute the NA values. So a lot of people, they find difficulty in imputing the values. So what you can do is you can make use of this pre-process function, and when you, this is nothing but the data set, right? This is the data set, and method is equals to KNN impute is what you are employing over here. It imputes the numerical data, right? Why does it impute numerical data, friends? Yes, any thoughts? Why does it impute only the numerical data? Why not categorical data? Why does KNN do not impute the categorical data? It is because there is a distance measure which is involved in employing your KNN algorithm, right? K nearest neighbor. Are you not calculating the distance measure in your K nearest neighbor? You are certainly employing the distance measure. The distance will be calculated between two numerical values, right? So when you have a categorical variable and a numerical variable, you cannot employ. Request you to please, everyone, please be on mute. and here there will be a problem. For that reason, what you can do is, before itself you can create dummy variables and then you can start off the imputation. Or else you may have to use, for these categorical variables, you can make use of mode technique or some other technique to impute the values. Now we will be concentrating on the numerical data using knn impute. So once you employ this knn impute over here using the pre-process function, what it does is it imputes all the na values, all the numerical na values in the dataset. It is going to impute and it is going to give you 0 NA values for the numerical.
I want to ask a question.
Yeah.
I want to ask a question. So does it take all the X variables and do KNN imputation, or does it?
Sorry, what was the last thing?
Does it take Y variable also?
Yes, it takes the Y variable because it doesn't know which is X and which is Y, right?
Okay.
So what you have to do is you can separate
Right.
the Y
Yeah.
variable and then you can just feed only the input variables and then you can employ this function, right? Because for Y variable of interest, in order to impute, for example, if you have got a lot of NA values for Y variable, that is taken care. There's something called as pseudo labeling using semi-supervised learning. Semi-supervised learning, you can employ this technique to impute or find out the values. It's like imputing your output variable. So using that technique, you can employ the output variable, and for the input variables, you can make use of any one of these techniques like your KNN imputation.
So the pseudo labeling is useful when the output, when your Y variable is categorical, and if your Y variable is continuous, then KNN impute can be used for the Y variable.
Yes, you can make use
Also?
of KNN imputation for your Y variable when it is continuous in nature.
Okay, thank you.
So here now what I'm doing is, after imputation you have to predict. Here, just here. So you're predicting the using the pre-process. Using this value, you're getting the pre-process values, and you're making use of this object over here and on this data set, which is going to give you the predicted values. So if we just run this line of code, since we do not have any, so in this data set it's not giving any values, but let me just, so this was not ran earlier. Once you ran this and once you run this line of code, you will be getting all the values, all the values get imputed. Then
So there is no model running command here?
Sorry?
Model? Your predict function is running the model by itself?
Yes, predict function will run the model with itself, because over here you already have declared the parameters over here.
Okay.
Okay. So once you are done with that, you will be getting the non-NA values dataset. Then you can make use of this non-NA values. So this line of code here, this I have used because earlier I was getting NA values for the categorical data. So I'm just using complete cases. All the rows give me the rows which are complete cases. Complete cases is nothing but non-NA values. So you can make use of this line of code and get the non-NA dataset. So finally, I'll be making use of this train underscore processed, and then there's another function to create the dummy variables. We know that we have to most of the times we create dummy variables. So you can make use of this dummy variables function over here. So dummy vars is the function, and if you just, this is our data set, right? So as dot, it's been converted to as dot integer in the interest rate, and wherever you have the factor variable, because this was a factor variable interest rate, so if we just employ dummy variables, it will create the factor variables also for your output variable of interest, which is interest rate. So in order to restrict it, I have converted it to as dot integer, and then I'm employing dummy variables on the data set. when you run this line of code, it will create the dummy variables. Now this full rank equals to t, it will be creating the dummy variables, but then it will not be displaying the dummy variables. I mean, for example, the concept of dummy variables is something like this. So in the output you will be getting, for example, if there are 4 levels of a factor variable like your interest rate, 1, 2, 3. So it will be creating the dummy variables interest rate 1, interest rate 2, and it will not display. Interest rate 3 will always be there, but it will not display it, because when you know the degrees of freedom over here is 3, right? Degrees of freedom is n minus 1. So 3 minus 1, that is 2. If you know this and this, anyways, third one will be 1. That is nothing but this full rank t. So using this function, you can employ dummy variables function, and it's going to give you the dummy variables. So let me run this line of code. Structure, you can see over here it has given 2 and 3, but it's not displaying 1, right? So in that way, wherever you have got any factor variable, it's going to create the dummy variables, and it will only display n minus 1 variables for that particular factor variable. Now dummy variables are being created. Again, you can make use of this create data partition from the caret function, and you can make use of this 80% of the data in the index. So from that transformed data, I'm making use of 80% of the data in my training data set. So I'm saving this in my index object.
Can you again explain? Can you explain train underscore transformed as a data frame predict? What exactly are you doing here?
Train and see over here we are creating the partition. We are splitting the data over here. In this line of we are just splitting the data over here. And if you have any questions, I request you to please post them using the chat window, and we will be taking up the questions towards the end of the session. Over here, what we're going to do is we are splitting the data. From this transform data, we are not predicting anything over here. We are considering 18% of the data in the training data set. Since that training, just for the sake of understanding, I have to employ all these functions from this training data set, original training data set. I have, what I did is I imputed NA values, created dummy variables, and now I'm dividing. Just consider this as original data set, and then over here dividing the data set into train and test once again. Got it? So this is what we are going to do over here. Now after you run this line of code, you will be getting index with 80% of the data. Just a moment, friends. Just a moment. I just use train underscore processed, and here as well, since I have not created any imputed any values, so I'll be using train underscore processed here and train underscore processed over here as well. So I am creating the training and test data over here. So train underscore transformed is nothing but, see over here, train underscore transformed I mean, you can just ignore this, over here. It's like this you can ignore this thing over here. Till here we are creating the dummy. I mean, it's like, you are creating an object dmy, and you're calling that object over here to predict, to just to make the create the dummy variables here. Using this predict function, you are creating the dummy variables. Now dummy variables, here you have the dummy variables. Now what you're doing is you're making use of this entire execution of the code over here, and the new data is your train underscore process. Once you do that, this is the object in which you will be having the dummy variables, right? So using, since I did not, there was an error message, so I'm not making use of the train underscore transformed. I'm making use of train underscore processed here, train underscore processed. So I have got the training data set, I have got the test data set over here. Now if you look at the training and test, just yeah, so you have got 949 observations, and probably around 940 200 observations in your test data set. Now feature selection, there's, you can select the features from your uh, RFE control is the function using which you can select the features. Now before RFE, actually RFE is the function which is used to select the features. Now here you have to define your input variables, you have to define your output variable, and you have to define this parameter RFE control. Now in order to, we know that we can define your input variables, we can define your output variables, and over here we do not know what is RFE control. So you can just, go to help over here and just do RFE. You'll get to know it is backward feature selection, the process how it eliminates the features and selects the this thing, the variables. So what happens is it will be multiple in multiple ways. It will be employing the model, and it will be selecting the features. RFE control. The documentation is present over here. You can just go through the documentation. So this control is executed over here. This is the object which is called from this function. Now RFE control of, if you just have to method, mention the method as repeated CV, which is going to give you, it's going to repeat the function 3 times, and it's going to give you the control. So if you just run this object, you know that the output variable is outcome variable, and the input variables is from the training data set. So what I'm doing is, from this training data set, I'm just excluding this interest rate, and I'm selecting all the other variables. So when you do that, you got outcome variable here, which you're declaring over here, outcome variable, and input variables, all the input variables from here, and our RFE control over here. When you run this line of code, you will be getting, take some time. Probably will take few seconds, I believe so. So let me see if we have any questions. You can go for k-folds or cross validation. I mean, both are almost the same. Sweta, you can employ it, and you will be getting, this thing, the reliability on the accuracy of the models. Sampling, Shanu, sampling is nothing but random sampling. It will be doing simple random sampling in your sample function, the normal sample function that you use. This is taking a long time. So if you just run this object, you will be getting the variables which have contributed. So the top 5 variables out of 16 variables which have contributed a lot towards is grade A, loan dot grade A, loan dot grade B, all these variables. These are the variables, different variables which have contributed towards the model building. This is a recursive feature selection based on cross validation using 10 folds, and it was repeated 3 times. Now there are different models which you can, there are more than 200 models in your Caret package, 200 machine learning techniques which you can employ. So this function names of get model info is going to give you the number of models that you can build. So there are more than 200 models that you can make use of. Any function that you can call. You have got AdaBoost, you have got different ones, Lasso, base, and you have got C 5.0, and lot of all the techniques will be, all the algorithms are present over here. You can make use of those functions, neural networks, random forest, all those things are present in one package itself. So here what you have to do is, again, you have to, in order to build any model or run any model, you just have to run this train function on the input variables, and you have to define your output variable over here, and you have to mention the method. So here let me just try to run it. If it's taking time, we'll stop it, or else we'll look at the output. So this is nothing but gradient boosting machine. It's an advanced analytics topic. If you run this code, so the package is required over here. It's installing the package. So these are the different functions that you can make use of, different models that you can run. And apart from this, by the time it executes this code, we'll try to look at the different other things which are possible. Okay, so it's running the model. So we have not defined how many iterations it has to complete, how many number of iterations. So it's making use of the default values that are present in the package. The model has been built. Similarly, let me just run this. You can run this as well. Not sure how much time it's going to take. RF is nothing but your random forest. You're trying to build a random forest. You're building different, for the classification technique. You're running different models, right? For in your real time, what you're supposed to do is, from the entire data set, if it's a classification technique, what you do, you run from the entire data set. You take some sample, right? Do a random sampling, or you can make use of credit or create data partition, and then you can derive some small data set. On this data set, you can perform different classification techniques, right? So you can make use of this package, and you can run all these models over here, and then also you can fine tune the parameters. So every function will have the parameters. Every function will have parameters that have to be fine tuned. It will take a long time if you manually do it. So there's a method over here which will automatically fine tune the parameters on its own. For example, let me just stop it over here. I will not run this random forest. It's already ran. So fine tuning the parameters using tune length. So what I'm doing over here is, my model, this, if you just do model lookup of model under equal to gbm, these are the parameters that you have to fine tune. N.trees, interaction dot depth, shrinkage, and this is the fourth parameter. So you have to declare these parameters over here. but you have not declared these parameters, right? You just have mentioned the name. So they have taken the default values, but you do not know whether the default values which it has taken, is it good for the model or not. So in order to fine tune that parameters, you can make use of this. Where is that? Here, over here, tune length equals to 10 is going to fine tune the parameters. But again, you have to make use of this train function. Within train function, you have to declare your input variables, you have to declare the output variable. There's another parameter called as train control, which is coming from here, and method is gbm, and tune length equal to 10. Now fit control is nothing but it's asking, what we are asking is, we are asking the function to do a repeated CV cross validation 5 folds is what we are trying to do. So this is being done over here, and we are calling that object in this particular line of code. So using cross validation and using the fine tuning of the parameters, in one go you're building a model and looking at the output. Sweta, you can fine tune the parameters in a default way, or also you can fine tune the parameters manually as well. This line of code is going to give you the parameters to know the what all parameters which are available for this model that have to be fine tuned. Now, if you're not aware of the parameters, if you're having any confusion, you can just make use of this line of code, and it will automatically give you the optimal values of the parameters. So be it any model, you can employ this line of code. Since it is a GBM classification technique, it's taking time. Once it is done, we will be plotting the model, and we'll be looking at the variable importance, and finally we'll be building the model, predicting the values on the tested data. Before it executes. So you have something called as variable importance over here. Again, it will display you the important variables that were being chosen in order to build the model. So if you just run this line of code, variable importance of object equals to model underscore gbm is going to give you the important variable that were chosen. And if you just do a plot, you will be getting a horizontal bar plot with the importance of each and every variable over there. So in that way, you can run the variable importance for GBM, RF, neural networks, and GLM, generalized linear model, right? Now, till here, you will be completing the variable importance, important variable that were chosen to build the model. So once it is done, you will make use of that model underscore GBM, which is running now, and you will be predicting the values on the test data, and you will be getting the predictions. So I just wanted to show that thing. So it's taking a long time. After you predict the values, you will be getting the actual values and the predicted values, right? You will have actual values and predicted values. So earlier in your linear regression model, where you had the output variable as continuous, you looked at the r squared value. right? How are you going to decide the accuracy of the model over here, friends? When you have classification technique, in classification technique, how do you decide on the number of on the accuracy of the model? How do you get the accuracy of the model? Variable importance over here is nothing but what all variables this particular function GBM model has chosen, important variables that have been chosen by the model. It is, you can, if you know the functions, outside the Caret package, you can make use of those functions, or else in Caret package you have this function available which is going to give you the important variable that were being chosen to run the model. So coming back to our discussion regarding the output accuracy of the model, how do you compute the accuracy of the model when you have a classification technique, classification problem statement, like your logistic regression or your any other, be it any other neural network or your SVM or knife base, yeah, KNN. How are you going to uh, look at the misclassifications, friends? Are you not going to look at the confusion matrix? Confusion matrix cross table functionality from G models, if you can recollect. G models was a package which we were using in order to compute the classifications and misclassifications in our different classification techniques. Yes, so you can make use of this cross table confusion matrix as well over here. You can make use of this confusion matrix here. So here you can see that predictions table of predictions is going to give you the count of predictions for each and every level 1 2 3, and then this confusion matrix is going to give you the confusion matrix of your model by comparing it with the actual values. So if it just stops, then we can just run this thing. Probably I should have decreased the number of cross validations. Okay, finally it stopped. So let us look at the output. So let us look at the important variables. So here I'll be running this line of code, plot of model underscore GPM. So friends, you can see there are different, you know, iterations that were performed, and in these iterations, towards the left side on the y-axis, you have got the accuracy, right? Accuracies are there. So accuracy will be 0 to 1, right? 100%, not more than 100% will you have the accuracy. And you have got the iterations on the right hand side. So it has gone till 500 iterations. So the which one has got the highest accuracy, friends? Which is the highest accuracy that we have got over here in this plot? From this plot, where is the highest accuracy and what is that value? Yes, it is clearly visible from the plot that there's some, you know, thing somewhere you will find the highest, which is that point which has got the highest accuracy. 0.72, right? Slightly above 0.72. This is the point where you have got the highest accuracy. So our objective is to get highest accuracy, is it not? For highest accuracy means correct classifications are more and incorrect classifications are less. So this is the point where you have got the highest accuracy. And how many iterations are required over here? 50 iterations, right? So probably the default value, if the default value was, suppose, just imagine if it was 100 or 500, you shouldn't have got for the default value of iterations. If Because if you just use 50 iterations, you're getting the highest accuracy. Got it? So in that way, and you have also got the maximum tree depth over here. So the maximum tree depth for a red color is 4. So for this parameter maximum tree depth, you can make use of this value 4, and for the boosting iterations you can make use of that 50. In this way, it is going to give you the optimal values of the parameter that have to be chosen. Otherwise, what we have to do is we have to do a trial and error method. Every time what you are supposed to do is you just have to do a trial and error method and look at what is the accuracy that you have got. So using this particular function, it's going to give you, it's going to compute all the things and it's going to give you the optimal values of the parameters. Now once that is done, we will be looking at the variable importance. Just a moment, there's something wrong over here. Just a moment. Let me run it again. There's some error over here. Not sure what exactly is the error. Probably we'll have to look at. So it's going to give you the variables which are important. Okay, there's some error over here. But anyways, what happens is it gives you the variable names which are important or which were important in building the model. That will also be given, and if you do a plot of that, you will be getting a plot something like this. First variable or any variable v1, or then you have got v4, v2, v3. In this way you'll have scores to that against 10, 20, 5, 15, something similar to this ones. You will be getting something similar to this, and you can decide upon the variable that have to be chosen in order to build the model as well. Now finally what to do is you have got the, you know the parameters, so you will be fine tuning. What you will do is you will make use of those parameter values and you will employ another model using that parameter values, and you will be coming up with a model. Now using that model that you build, you have to define over here to predict the values. Now using that model you're predicting the test values. So this is my test data, this is my model that I have built, and this is my predict function, predict.train, which is coming from the Caret package. Type equal to raw, I believe it is for your classification technique classifiers. So when you do that, you will be getting predictions. Now when you do the table of predictions, you will be getting, see, 101, 80 and 53. For first classification 1, you're getting 101 observations. For 2, you're getting 80. For 3, you're getting 55. These are the number of observations. When you do a confusion matrix, you have got all the values over here. So here in the confusion matrix, these are nothing but your correct classifications. These are your correct. 82, 52 and 37 are correct classifications. 11, 11, 17, 8 and 10 are incorrect classifications. Now you can compute the accuracy. You have got 72.46 accuracy, right? 0.7246 is the accuracy that you have got, and you have got a p-value which is very less than 0.05, and also you have got the sensitivity value, specificity value, all the values that you have got from the confusion matrix that you can compute. All those values will be computed over here itself. Let me Erase everything. Yeah. So here you get all these values from this particular function. So just running confusion matrix is going to give you sensitivity, specificity, the p-value, and the accuracy. You don't have to run the accuracy once again by defining another function. So within confusion matrix itself, you'll be getting all the values. So this is what we have, friends, from Caret package. So there are more number of functions which are available. The time does not permit to discuss all those functions. You can just go through all the functions and you can make use of these functions, in which which is very helpful, so that you don't have to run the functions on your own. You can make use of these functions and you can evaluate the models. Any questions or any doubts so far? Yes. All right. If you people do not have any doubts, we will call it a day and we'll end the session over here.